So we'll continue double velocity estimation. So remember, we have a potential outcome model. So this is the linear regression potential outcome model, and then optimal APW estimator can be written as some kind of a double robust form, right? So then we have a prediction plus a residual and weight inflation. Same thing here. Okay. And yeah. And then regarding the choice of beta hat, we can consider some kind of a weighted least square, and then then the double velocity estimator. So this is a linear in y in yi. So this is a linear. So everything is linear in yi, and then you can compute. So find the weight, right? So this is the final weight. And then first thing is that regarding the choice of QI, we may so this is the result is arbitrary, right? This result holds for any function, but you may wonder what would be the best choice, and that depends on which model you are talking about. If you are using a PS model, then you may use this optimal weight is minimizing something like pi I hat 1 minus pi I hat I minus 1, right? So this is a kind of square. So that was what we covered last class. So in that case, this is your QI inverse. So that's this choice. Another choice would be just to use the model, outcome regression model. And then if you use the outcome regression model, then QI is the model variance. So that's for optimal choice, but the result here we don't really care about a particular choice of QI. This is more general. One thing you can check is that this weight here, right? So the proposed weight here satisfies this. So that is a covariate balancing property. And then I think we covered this several times, but let me do it one more time. So this is equal to pi I hat inverse plus x total, right? X minus x hat IPW W. And then this guy TI QI inverse xi prime inverse times xi QI inverse, right? So if you apply it, then the first okay, and then that means you want to, I guess, then you have two terms, right? So this guy applied to here becomes a IPW, right? Is just equal to 1 to n TI I hat inverse xi. So that means you have a cancellation. So if you apply it here, then you have a cancellation. And then if you apply summation, right? If you apply summation TI xi, then this guy and this guy cancels. So you end of the day, you will get this guy. That is the feature of regression weighting. Okay. So and as long as the weight satisfy this balancing covariant balance property, then the properties, so using the weight estimator is a model unbiased, right? So under the model that we covered that already, but let me do it one more time. So I guess this is what we want. I guess you want where you want bar. It's just the one over n. So then this is essentially Ti omega I 1i or 1i yi minus and then because of this this is actually y1i, right? And then this guy is xi prime beta 1 plus ei 1, right? So you get something like we keep repeating. I think we covered this many times. So basically, right? Then this is 0, right? So this is a condition. So if this is 0, then the mean part disappears, and second part is not equal to 0, but 0 in expectation. So that means this is 0 in expectation, right? Equal to 0 in expectation. So that means it is model unbiased. Okay. So that is the note here. And now this AIPW estimator in 3, okay, this guy, right? So if you look at this is a prediction, right? Prediction. And this is bias correction. So that's one interpretation. So you have a model prediction, and then the model, if the model is incorrect, then we may have a bias, but we can estimate the bias using Professor's group function. So so that is the idea. But then this bias correction is added, right? You have a bias correction added to the prediction. So that's what this message is. Bias corrected prediction estimator, where the bias correction term is added externally. And now we want to consider an alternative approach that implements bias correction internally. So what that means? That means we don't really add anything extra. Okay. But we want to impose that bias correction constraint into the estimation of the regression coefficient. And how can we do that? Well, so basically, this prediction estimator is bias corrected automatically if this bias correction term is equal to 0, right? So this is the bias correction term. And if the bias correction term is 0, that means this prediction estimator is already bias corrected. Okay. Now, then the question is how to achieve this goal, right? How to achieve the condition 6. Okay. So the condition 6. So basically, condition 6 is the sufficient condition for a prediction estimator to be bias corrected or doubly robust. Okay. So, well, this is kind of similar to our homework problem. Basically, what is the beta hat? One. Beta hat one is a definition of a beta hat one is Ti, Xi prime, Qi inverse times to one Ti, Xi, Yi divided by Qi, right? So that is the definition. Okay. And so that means you can actually so this one means that you have a you can just rewrite the estimation formula right. You can write, if you solve this, then you will get this. So that means this is indeed definition equation for obtaining beta hat one, which is indeed can be written as this. So this is equivalent to this, right? Because we have something in common here. We have something in common here. So then all you have to do is to, move this part to here. So that is basically this one. So in fact, this is actually normal equation, right? This is the normal equation for obtaining theta hat one. Now, what's the next step? So next step is to, okay, figure out a condition that leads to this. So how can we achieve this guy from the definition? Okay, so how? So notice that this is actually a vector equation, vector equation, while this is a scalar equation. So basic idea is you first transpose. You first transpose. Okay. and then post multiply by a both sides, right? Then if you, because x prime a is a qi divided by pi I hat, that means this guy is equal to qi divided by pi I hat minus 1 over qi. So then qi cancels. That means you get this one. So this is actually the first term of 6, right? Because 6 is this one. So basically you have a residual and pi pi divided by pi I hat is equal to 1. So that's basically this one. You have a residual here, and then pi divided by pi I hat is equal to 0. Okay. So basically, we assume one more thing, right? The assumption is that x prime a is equal to qi divided by pi I hat for some ai. That means what? That means this guy, right? This guy is a part of xi. Qi divided by pi I hat is a part of xi. Or you can say that, okay, we augment x. We augment x to include this guy. So you augment your covariate. So that gives us to consider this optimization problem. So this is actually the same constraint that we consider to obtain weighted least square, but then in addition to the original calibration condition, which is 5, right? This is the original calibration covariate balancing condition, original calibration condition, plus this guy, because this is a part of x. So if this condition holds for some a, then condition a is not really necessary because it's a part of original calibration equation. But if not, then we need to include this additionally. So this is original calibration, right? This is a calibration constraint or covariate balancing. And then this condition can be called the internal bias calibration condition, in the sense that we do bias correction internally. Okay, let me so let's solve this. Okay, so basically we want to minimize q omega is something like this, ti omega I squared qi subject to ti omega I xi and right. Okay, so how to solve it? Well, Lagrange multiplier, right? So we want to consider Lagrange multiplier. We have two constraints, lambda 1 and lambda 2. So then we have something like this. This is a vector. Uh, so that is the Lagrange multiplier. And then you solve this, right? So if you do that, then so you may want to use this one. And then basically this guy is equal to Ti omega I Qi plus lambda 1 prime omega I disappears, and so you have Xi, and then omega 2 Qi equal to 0. And then actually you can probably better ways you just use minus. Doesn't really matter how you call it. So if you do that, then actually you sorry to be more rigorous, we have if you have a Ti here, then we have Ti here too, right? So Ti, but Ti can cancel. So then that means I is lambda 1 Xi divided by Qi plus lambda 2 1 minus I have. So that is the solution. You also need to estimate the lambda. Okay. So this regression weight essentially is a linear function of the property that you use in the calibration. That's it. Okay. So that that leads to this. That's how you get this. And then what is the lambda 1, lambda 2? Where lambda 1 and lambda 2 that can come from? Well, they can come from the calibration equation constraint. And the constraint is essentially these two constraints, 5 and 8. So 5 is the calibration constraint, and 8 is the IBC constraint. So this is the calibration constraint with respect to X, and IBC constraint is this one. And then once you write down that way, then you can see, then you can take a look at what is the nature of this equation. The nature of this equation in terms of lambda 1 and lambda 2 is a linear equations, system of linear equations. So that's you know how to solve it, right? This is just a linear equation. Then you can actually use the matrix algebra. So basically 10 and equation 10 and 11 could be expressed in terms of the using the matrix algebra. So that's it, right? So you get you now write down as a matrix form and then solve it. Okay. You see, so once you right, so this guy is then you know, this is really simple linear, right? And so and then point is that you this is actually you can write it this way. Oh no. 2 x1 qi pi I hat inverse, right? So you can write this way, or you can write this is a scalar, so you can actually transpose it, xi prime divided by qi times lambda hat 1, right? Plus, okay, I guess probably this is better. Pi I hat inverse lambda hat 1 lambda hat 2. Scalar, so you can scale. And then all you have to do, so this is, oops, this is known, right? This is known. And this is a known parameter, right? But this is actually parameter. And this parameter is a solution to this equation, which is a solution to this equation. So that means this is indeed lambda hat prime, right? If you write this way. So if you write this x and this guy as, so here, right? Then this is so we use this form. Okay, so that's just a metric set. Or even you can actually simplify it further by introducing another notation, z. Okay, so let's just say, call it z. Gi divided by qi. And then everything could be just written as a very simple form. Then z is what? Z is the variable that we use for calibration, essentially. Right? So yeah. C is the variable that we use the calibration. Qi is the variable that we used in the objective function. Right? And then this is basically the solution. So that give us some, now, so this is the form of the weight. And now we want to plug into, right? So this form, use this form into the estimator, calibration estimator. And then this is actually, right? You have this form. So that is a linear form. So this is a regression rate. And then lambda can go outside the summation. Lambda can go outside. So you can move this one outside the summation. Okay. And then simplify. So this, then you have this guy. And this is lambda outside. Right. And then lambda hat is actually is this form. So then you can actually have this way. And then once you combine these two, and this is a regression coefficient. So then which is actually prediction point. So this is fundamentally important. We've been using this many times already, but bottom line is the calibration weighting estimator is algebraically equivalent to a prediction estimator. So here, I didn't use any statistics, right? I just used a matrix algebra. That's it. So then, but the interpretation, right? It should be a statistical interpretation. So this is purely algebra, but we know that this is basically we have a calibration. We have constructed calibration weight by solving some optimization problem that could be interpreted as a prediction estimate. And now, remember this G. Okay. So Z is different from X, right? Because Z include the additional component, which is this guy, right? So we introduce additional notation to emphasize that we have augmented covariance by including this term. And why we include this term? Because we want to achieve some nice property, which is bias correction term is equal to 0. That's right. Because we want to achieve the this one, which by so so that is what I'm going to show. Basically, this is the definition, right? This is the definition of gamma hat, and gamma hat is nothing but a solution to this. So probably maybe difficult to derive this one, but if you this direction should be easy, right? You know how to solve this one to get this one, right? So this part is easy, but this is should be equivalent. So okay, so once you have this one, then you recognize that QGI contains what? QI divided by pi I hat, right? CI, so QI divided by pi I hat is a part of ZI. So that means I can consider that component. So that means I can, because so this is a equation of vector equation, right? So system of equation. At least one component should have this one in it. So that means you QI cancel, then you have this one. So that means you are actually satisfied this, which means that what? Which means actually the bias correction term, equation 6. Bias correction term is equal to 0. So that means what? Because of 13 now, right? 13, the so this is 0, basically. So 13, equation 13 means this second term is 0. Whereas correction term is 0, algebraically equal to 0. But this is a doubly robust estimator. Doubly robust form. So now what we are saying is that we proved this one already, right? We proved this equivalence already. Equivalence due to page here, result 10. Result in page 10. So result in page 10 shows the equivalence between these two. And equation 13 shows that the bias correction term is 0. So that means combine the two. That means the proposed calibration weight is indeed bias doubly robust. So you can see if the outcome model, right? So now let's take a look at this equality more carefully and try to understand the meaning of doubly robust. Okay, so if the outcome model is true, right? If the response model is true, then this will cancel, right? PS model is true, then this will cancel, and then this is so unbiased. So basically, the additional term does the bias correction, or bias correction of the prediction estimator or W robust using PS model. Okay, so PS model is incorporated here as an additional covariate. But now, what about the other direction, right? We are talking about the union of the two models. So outcome regression model and PS model. So if the PS model is correct, then this term help you, right? If the PS model is correct, then the second term will help you to correct the bias. But what about the other side? If this part is really correct, okay, that means what? That means you are actually, this will, that means your expectation, right? So, so this guy will convert it to, so this is a prediction, but the additional, so what is the model? What the model is xi prime. The true model is, so the outcome model is that xi prime beta 1 plus e1, something like that, right? So if this is a true model, that means you can write your model as 2i divided by pi I hat times 0. Right? So the equality, right? We have equality because we just added a 0. But the point is that under the true model, I mean, under the reduced model, under the model outcome model here, so if this is a true model, and if we fit augmented model, if we fit the augmented model, then the regression coefficient in the augmented model will converge to the true model, right? So that means the true model. So what is the true coefficient? The true coefficient is this guy, beta 1 and 0. So that means beta hat 2 will converge to 0. So so that means you are actually estimating 0. So the gamma hat 2 is the additional price that we pay to achieve the W robust. So here's some, key point. So if this is true model, and let's take a look at what is expectation. So expectation is that, okay, what is the gamma hat? Gamma hat is what Pi Ci, right? Ci prime Qi inverse Ti Ci Yi Qi, right? So that is the definition of gamma hat. And now I'm going to take the conditional expectation on Y. So because of Ti, this is actually 1, right? So Yi1 is the true model is xi prime beta 1 plus ei with the ei1 given x is 0. Okay. So I'm gonna take the, so then right? So that is the gamma head. And then the expectation of the gamma head given x is just the same thing here. And then right? And now all you have to do is simplify the algebra. So now the question is, what is ci prime by qi inverse? How to simplify it? So we want to show that this is actually 1 and 0. We should to show. So that's what we want to show. Because to show this one means that we want to show this. Notice that ci is what? Ci is xi, right? And additional term, which is qi divided by pi I hat. So how to show this? Well, you can show this by without really computing the inverse. How? You can just check the apply. All you have to do is to check the algebra here. Okay, maybe here. Right? We just what I did is I moved this one to here, right? I post multiply this one. But this is actually trivial, right? Because this is, what is this? This is xi prime beta 1 by the definition of this guy. We are done. So this guy is indeed the probability limit of the gamma head, right? So gamma head will converge to the expectation, and the expectation is equal to this guy. So that means the gamma head 1 will converge to beta 1, gamma head 2 will converge to 0. So that is basically what here. Okay, so that is all about the algebra actually, and some statistic. And now we're gonna move on to some more interesting problem of the how to discuss how to derive the asymptotic property of the doubly robust estimator. So it's a little bit tricky because when we talk about probability, we are talking about the model is a union, right? The model is a union of the outcome model. If you have a single model, then it's actually relatively easy. But here the tricky part is that we are thinking of a union of the two models to refer to the probability distribution. Okay, so we are interested in investigating the asymptotic properties of the calibration estimator, right? Where this omega hat one is obtained by minimizing the calibration problem with the two constraints. One is the calibration constraint, the other one is the IBC constraint. And we know that in the least square loss, squared error loss, we have a closed form, linear form of the weight, and which gives a linear equation for calibration weight. The tricky part is that Zi contains Xi and pi I hat inverse, right? I mean Qi. So Qi, you can say that Qi is a function of X, but pi I hat is a function of a parameter in the propensity score model. So then we need to consider certain equation for phi. Okay, phi hat is a solution to this equation. Now, how to solve the how to discuss the property? Okay. So let's clarify the parameter of interest and noises parameter, things like that. So it seems to be that we have one noises parameter, which is lambda. So lambda hat is a noises estimated noises parameter that determines the calibration weight, right? Omega I hat is a calibration weight, which is a function of a lambda hat. And this lambda hat is a solution to estimating equation, but C is a function of a phi I hat. C is a function of phi hat. So that means phi hat. There's another noises parameter, which is phi hat. So we have two noises parameter, lambda and phi. And then it's kind of a nested structure. I mean, not nested. So lambda can be computed given phi hat. And then we want to linearize. So we want to do tail expansion. Okay, and then assume, so under some nice conditions about the equations, lambda hat and phi hat will converge to a unique number, right? Unique value. So let's call this converge the limiting point to be lambda star and phi star. Can be anything, but we can just call it for now. And then try to apply the Taylor expansion. And then how to do Taylor expansion? Well, this is not really the standard form, but we know that this will be something like, so okay, lambda hat and phi hat is mu hat lambda star phi star plus something like this, right? This is a typical formula. This is a typical formula. But what is this? This is actually come from the this should have come from the equation that determines, right, estimated equation that determines the lambda hat and phi hat. Because, let me see. It's 0. And then we take take a Taylor expansion. Something like that. So end of the day, so this is a coefficient. So this guy is proportional to this guy. So to simplify, we can just write it as a original function, right? So this is the original function, and then we have a limit, and then we have two estimating equation. So the expectation, so that they will be a 0 in expectation. And all you have to do is to find out the coefficient, gamma star and kappa star. And that is satisfies the Render's condition. The Render's condition is nothing but the condition that determines the, so, okay. The key part is that this is original nuisance parameter, right? This is the original nuisance parameter, lambda and phi. But instead of using lambda original parameter, we use a different parameter. It's kind of dual parameter. Gamma and kappa. And transfer the transfer the uncertainty in gamma hat and lambda hat phi hat to the uncertainty in gamma hat phi hat. So basically once you view it as a equation. So this is lambda Render's condition. Basically means if this is indeed linear, so the idea is if this guy is indeed really the correct linearization, that it should no longer depend on lambda, right? Partial derivative. So the partial derivative should be with respect to noise parameter should be equal to 0 if they are indeed linearized. Okay, so that is basically the condition. And then because we know the form, right? Because this is the form. And the form is not really difficult because you can actually, so this equation is equivalent to this equation. So this is star and double star. So this is the star. And this is double star. Okay. Good news is that this one is independent of lambda. The second equation. So then so the equation 15 is a little bit simpler than equation 16. Okay. So that is the probably best way to compute the Taylor expansion. Otherwise, it's very difficult because you have a parameter depends on another parameter. So then how to do linearization, that's very tricky. Okay. So now let's take a look what's going on. So let's take a look at equation 15. Let me, before we, okay. Let's first take a look at this one more carefully. So because we know the form, we know what mu hat is, what u1 is, what u hat 2 is. So we just write it. So this is mu hat 1 kel, and this is u hat 1. This is u hat 2. And u hat 1 and u hat 2 are all linear functions. So basically this is a summation, right? You look at this. They are all single summation here. So then you can actually write down everything. It's a summation of eta I. So that's the end of the day. So what is the eta I? Eta I is zi prime gamma star plus omega I star yi minus zi. Of course, this is actually y1 gamma star plus 1 minus ti I star hi kappa star. So this is basically eta I. So this is already linearized version. And so that means you can use this if you can estimate lambda I hat, then you can apply variance estimation. So computing the variance estimation itself is relatively easy. More tricky part is to understand the in under each model. So now this is the form of the eta I, and then let's take a let's interpret each equation. So what is this? So this guy, okay. So so what is okay? Wi star is a linear function of lambda, right? So if you take a Taylor expansion with respect to lambda, then lambda disappears, and so this is the only one. So this guy is nothing but round lambda. You had calibration, one not you, mu. This guy. And then what is this? Is you had one, this one, lambda, you had one lambda star. Because this is this guy, right? So this is you had one. And if you take the lambda, take the Python into lambda star. So as a function of lambda, lambda is just a linear function of lambda. So then you do have a very simple form. And so the definition of a gamma star is a solution to this equation. But gamma hat here, 612, is actually, so what is gamma hat? Gamma hat is just gamma hat is this guy. 1 and 2. 1, 2, right? So this guy inverse of this guy. So that means gamma the gamma hat in 12, this guy is already indeed converted to gamma star to solution to here, regardless of the model. You don't really need any model to show the convergence. So equation 15 is relatively easy to check. Now, what about equation 16? So what is the form of the kappa star? So kappa star can change for each different model. So okay, basically outcome regression model and PS model. Outcome, if under this model, kappa star is actually this. This way, this is no, it's something else. So that is so correct PS model, kappa star has a different form, 19. So this is actually 18, 19. So kappa stars are different. And so here's a kind of so this is the eta I, the form of the eta I that we already computed. And then if the outcome model is correct, what we know is that this guy will converge to this guy. And this guy will converge. So this is 0. Kappa will be 0 by 18. And this one is by I think I covered this before here, right? So that is page 13. That is the limit point for outcome regression model. The PS model will show that this weight will converge to inverse propensity through response probability. So for each case, they have different limiting point. So let me come back. Okay. So once you this one involves some theory, I mean some algebra, but suppose we accept this, that means what? That means this guy will converge to 0, right? And this guy will converge to xi prime beta 1. So you end up getting something like this. Okay. That's the outcome model. So then all you have to do is compute the mean and variance. Under the mean and variance under the outcome model. So under the outcome model, this is second term is 0 expectation. So then the first part is the mean part, right? So that is unbiased. What about the variance? The variance so what is random? The randomness is actually so we fix t and just treat the randomness in expectation respect to y. So then if you take the expectation, then this one is 0, then you have this one left. So that is the first part is this one. And second part is the variance of expectation with respect to y given x, right? Basically. Variance of y given x. So that's the formula. And then the expectation, so outcome model is that you basically you have this guy variance. So that means you have a omega I square term in it. So that is the formula for variance under the outcome model. And then the weight is indeed this form. Okay, so now let's try to interpret it. So the first term it's just the true mean part, right? So this part is you don't have to worry about the first term. Second term is more tricky. So okay. So this is actually, if you look at the variance, this is actually square, right? So that means if you include more x variables, then this will increase, right? Because you have a more. You are actually adding square terms, so that this will increase. But if you include some important x variable, then this will decrease because it's a model error, right? So you could consider different models, but if you including x variable will increase weight, including important x will decrease the variance, including unimportant x will increase omega star, but without decreasing variance. So for example, okay, for example, if your x is actually your model, suppose your model, okay, suppose we can include this. So this is actually model, right? I mean, we have this model, but suppose some part of beta is 0, right? Beta can, so when we write this way, that doesn't exclude the situation with the 0 coefficient, right? Some of them could be 0. So for example, you can actually x1, 1, beta 1, 1, you could write this way, right? If you could write this way. And then suppose the true value of beta is 0. Okay. Suppose this, so this is beta can be anything. So let's assume that we happen to have beta 2, right? The coefficient for x2 is indeed 0. Okay, then that means what? That means, okay, if I include x1 into calibration, right, then this is the signal part. So that means the variability in y can be reduced by including, right, this part. What about including this one? This one does not, if I include x2, the coefficient to x2 is 0. So that means it doesn't really have any impact on this variance. But it, including this x2, will actually have effect on the weight still, right? So that means you are actually increasing weight without gaining anything for that situation. So that means it's better. I mean, if the outcome model is under the outcome model. And now let's move on to the correct PS model. And then The problem is, so this is the weight. And we know the weight supposed to satisfy xi into something like that. But this is under the true correct PS model. This is will converge to pi I inverse, and then we want this to be true. That means the coefficient will converge to 0, and this will converge to 1. So because of this. So that's actually same as a design based. So in the design based, we are talking about here. If you assume a correct PS model, we are doing design based idea, and so then means we have a uh we use this one. So then kappa doesn't really change disappears, but the weight is simplified, and then we can actually show that this kappa is indeed this one. I have some proof for these two results. You can take a look, and I may explain a little bit further. Okay, I still have time. So once you do that, then this is actually kind of two-phase sampling, right? We are under the correct PS model. This is just a random second phase. Ti equal to 1 is essentially second phase sampling. So we can apply the same theory for two-phase sampling to get this result. So that is basically variance of conditional expectation. Now the conditional expectation is this guy. Okay. So the conditional distribution is T with respect to T. So for this one. So if you take the expectation, then this one cancels, and then everything cancels, only y1 only left. So that's why we have this one. And then variance, you have that's the usual two-phase thing. We have something comes in, and so here's an interesting interpretation. So if the outcome response model is incorrect, so okay, we are talking about the union of the two models, but outcome, suppose this is not really correct. Outcome regression model is incorrect situation. That means the inference should be evaluated under the PS model. So that means this is the correct variance when outcome model is incorrect. So that means we actually have a gain in efficiency because by augmenting. So that means bottom line is, okay, if you compare this guy with all the way, maybe I will explain further. All the way to here, the very, okay. This is actually, this is like, so here's a one estimator, right? This is the more like a textbook type doubly robust estimator. And another one is, I just explained, augmented regression estimator. So if the response model is correct, and I mean outcome, so the difference, we have two estimators. One is this one, the other one is actually using the augmented, right? And you may wonder which one is better. So if the outcome regression model is incorrect, then this one is better because of the additional covariance. So that is the basically idea. But I will maybe I will explain more in the next week. Okay, I think that's all.